Hello everyone, welcome to another video. In this video we're going to be covering the midterm, so we're not going to be reviewing any new material. So with that said, let's get started. So in question 1, we're given information about a study conducted by those at the Mayo Clinic, in which they're investigating the relationship between obesity and the energy spent on daily activity. Here we have a table with some summary statistics about the investigation. Here we see that there are two groups, one lean and one obese, with observations from 10 volunteers per group, and the response variable is the average time spent standing or walking. So let's go ahead and look at the first part. Here we want to know if the sample data is a random sample. We know that the observations were recorded from volunteers for the study. So to answer A, we answer no, because the data is captured from volunteers and not randomly sampled. As for part B, we want to test the homogeneity of variances. So to start, we define our null and alternative hypotheses. The null in this case is that the variance for group 1 is equal to the variance of group 2. The alternative hypothesis, on the other hand, is that the two variances are unequal. To test for homogeneity, we derive our F statistic. The F statistic is simply the larger sample variance over the smaller sample variance. In this case, we are given the standard deviation, so we square our standard deviations and derive the test statistic. Then for any statistical testing, we either derive a p-value or derive a critical value. In this case, we're going to go ahead and derive the critical value. To do so, we look at the F distribution with degrees of freedom 9 and 9, because both samples have a sample size of 10, and our degrees of freedom are calculated by subtracting 1 from the sample size of the corresponding groups. We then look at the critical value in the corresponding table. Here we want an upper tail with area 0.025, or equivalently a lower tail with area 0.975. As a result, we find a critical value of 4.03. So therefore our decision rule is that if our test statistic is greater than or equal to 4.03, we reject the null hypothesis. With that, we can conclude that the population variances are in fact equal because our test statistic is below the derived critical value. And with that, we're going to move on to the next question. We are asked to analyze whether lean people spend significantly more time standing and walking than obese people on average. First, we define the parameter. In this case, we're looking at the difference between average standing and walking times between the two groups. Therefore, our parameter, we have mu1 minus mu2 equals the difference in population mean times spent walking or standing by lean and obese people. Then we construct our null and alternative hypotheses. In this case, our null hypothesis is that mu1 minus mu2 is equal to 0, and our alternative hypothesis is such that mu1 minus mu2 is greater than 0, because we're trying to decide whether mu1, or the mean associated with the lean group, is significantly larger than mu2. We then have to look at the assumptions for the analysis. In this case, we're comparing two small independent samples assumed from normal distributions. Additionally, we assume equal variances for the populations as well. Next, we compute our test statistic. To start, we must calculate our pooled variance. Since the sample size of both groups are equal, the pooled variance is calculated by taking the sum of the sample variances, then dividing by 2, all under the square root. That results in a value of 89.529. With that, we can calculate our test statistic. Our numerator is the difference in mean between the two groups, and the denominator is the pooled variance times the square root of 1 over n1 plus 1 over n2. This results in a test statistic of 3.8. Finally, we need the degrees of freedom for our t-distribution, which is the total sample size minus 2, for a total of 18 degrees of freedom. Next, we calculate our critical value for our decision rule. In this case, it's an upper tail test, so we find the value associated with the 95th percentile of the t-distribution with 18 degrees of freedom. This yields a critical value of 1.734. Therefore, since the test statistic is greater than our critical value, we reject the null hypothesis, and we can conclude that based on our two samples, both of size 10, There is significant evidence at the 5% significance level to conclude that lean people spend significantly more time standing or walking than obese people on average. All right, so moving along to problem 2. Here we have a research project where 10 subjects were shown an emotional video. They then had a PET scan on their brain while they were being tested on their memory of the video, their memory scores, as well as their relative amygdala activity are reported in the table. So first off, we're asked to assess the scatter plot. From the scatter plot, we can make the following assumptions. First, the relationship seems to be linear. The points seem to follow a linear trend and aren't scattered chaotically around the plot. Secondly, there seems to be a strong relationship between MS and RAA, as there doesn't seem to be any points that lie outside that linear structure. Lastly, we know that there's a direct relationship between MS and RAA because the slope is positive, implying that as RAA increases, so too does MS. Next, we must calculate the correlation coefficient. Given the table, we can calculate the correlation by first having the covariance of x and y in the numerator. This is the value found on the off diagonal. Remember that the main diagonal features the respective variances for the two variables. Then in the denominator, we have the variance of x times the variance of y, then both under the square root. That division gives us the correlation coefficient of 0.6768. Next, we can move on to the analysis whether the two variables are correlated. Our first step is to define the parameter in the null and alternative hypotheses. To start, our parameter here is rho, which is the population correlation between RAA and MS. Then our null hypothesis is that rho is equal to 0, and the alternative is that rho is greater than 0. Then, since we're testing at the 5% significance level, we know that alpha is 0.05. We then can calculate our test statistic. Here we have our test statistic of r times the square root of n minus 2 over 1 minus r squared, where r is the correlation coefficient. This gives us a test statistic of 2.6. Furthermore, our decision rule is such that we reject the null hypothesis if the p-value for our test statistic is less than alpha. In this case, we're given a p-value of 0.0316, which is the combined area in both tails. So in the upper tail, we have an area of half that value. So we have a p-value in this example of 0.0158. Therefore, we can reject the null hypothesis, and since our p-value is less than our significance level, we can conclude that rho is not equal to 0, or rather that the two variables are in fact correlated. All right, and moving along to the next question. We have a study that was conducted among college students who smoke. The intent of the study was to determine whether there exists a relationship between the number of cigarettes smoked per day and the smoking status of their parents. The smoking status of the parents were divided into 3 groups: never smoked, former smoker, and current smoker. The data is summarized in the table here. So on our first question, we are asked to determine whether there's a significant difference in the mean number of cigarettes smoked per day according to the parent's smoking status. And we're going to be running this analysis at the 5% level. The first step in the analysis is to define our parameter. In this case, it is mu j, where mu j is the average cigarette smoked per day by members of group J, where here j is the index for our groups. In this case, j equals 1 is the index for the never smoked group, j equals 2 is the index for the former smoker group, and j equals 3 is the index for the current smoker group. Next is our null and alternative hypothesis. Our null hypothesis is that mu1, mu2, and mu3 are equal. The alternative hypothesis is that not all of the means are equal. And then lastly, we have a significance level of 0.05. We then assess the conditions necessary for the ANOVA analysis. These conditions are independent samples from a normal distribution with equal variance. Our test statistic here is a bit involved. First, we calculate the means square between. The numerator is the sum of the sample size per group times the square difference in the sample mean and the overall mean for the three different groups. The result is then divided by the number of groups minus 1. This results in a value of 732.87 over 2, or 366.4. Next, we calculate the mean square within. This is the sum of the respective sample sizes minus 1 times the sample variances. It's then divided by the total sample size minus the number of groups, in this case 3. The result is 1,691.4 over 114, or 14.84. Finally, we calculate the F statistic by dividing the mean square between by the mean square within for a value of 24.7. We can devise a decision rule by comparing our test statistic to our critical value. Our critical value in this case is the 95th percentile of the F distribution with degrees of freedom 2 and 114, which is a value of 3.07. Our corresponding decision rule in this case is that we reject the null hypothesis if F is greater than 3.07, and since our test statistic is greater than our critical value, we reject the null hypothesis. Therefore, since we rejected the null hypothesis, we can conclude that based on a sample of 117 students, there is significant evidence at the 5% significance level to conclude that there's a difference in the average number of cigarettes smoked by students in the three groups. Next, we're asked to calculate the R-squared value. And to calculate the R-squared value, we simply divide the sum of squares between by the total sum of squares. This yields a value of 0.302, or 30.2%. Then finally, for part C, we construct a Tukey multiple comparison procedure to compare the mean number of cigarettes smoked per group. To do so, we need to find the mean square error, in which we found earlier. The next value is the value for Q, which we need to find the value from the studentized range distribution table. In this case, it is 3.365. So with those values, we can calculate the confidence intervals. The interval is calculated by taking the difference between the mean of the two groups, then adding and subtracting Q over the square root of 2, times the square root of the mean square error, times the sum of 1 over the two respective sample sizes. So as you see here, we see that there are 3 different confidence intervals. That way we exhaust all the different comparison options. So after calculating the 3 different confidence intervals, we can make observations about the range. Since we're testing here whether the difference is or is not equal to 0, if 0 exists inside the confidence interval, we cannot reject the null hypothesis. However, in the case for the comparison of groups 1 and 3 and 2 and 3, we see that 0 is not within the confidence interval, so we know that the groups are significantly different. In this case, we can conclude that group 3 is significantly different than the other two. So moving on to problem 4. In our final example, we have grades from a random sample of students who have taken statistics with a certain professor over the past 20 years. These grades were used to estimate the relationship between grades on the final exam and the average exam score for the 3 exams given within the term. We then have an output, presumably from a SAS analysis. First, we need to find the value of the sample correlation coefficient. Since we're looking at a simple linear regression model, the sample correlation coefficient is the square root of the R-square value. In this case, 0.7238. As for part B, given the sign and the magnitude of R, we can conclude that there is a strong, direct, linear association between the final exam and the midterm average. Then here in part C, we are to formally test whether the two are correlated. To start, we must define our parameter. So here we have parameter rho, which is the population correlation between the final exam and midterm average. Then our null hypothesis is that rho equals 0, and our alternative is that rho is greater than 0. Finally, our alpha is 0.05 because we're testing at a 5% significance level. Our next step is to calculate the test statistic. As we saw in an earlier example, our test statistic when testing for correlation is r times the square root of n minus 2 over 1 minus r squared. This gives us a value of 13.99 under the t-distribution of n minus 2, or 178. Next, we devise a decision rule, but first we need to calculate our critical value. In this case, we're looking up the 95th percentile of the t-distribution with 178 degrees of freedom. That results in a critical value of 1.665. Thus, our decision rule is to reject the null hypothesis when our test statistic is greater than 1.665. Furthermore, since our test statistic is nearly 14, we reject the null hypothesis, and we can conclude that based on a random sample of 180 students, there is significant evidence at the 5% significance level to conclude that there's a strong, direct, linear association between final exam score and midterm average. Next, we have to fill in some blanks. Here it's asking for the response variable, which in this case is the final exam score, which is a numerical type of variable. Then our explanatory variable is the midterm average, which, like the final exam score, is also numerical. Our next question asks to write the appropriate regression equation. If we navigate to the output provided at the top of the question, we see the estimated coefficients. We see a value of 16.6 for the intercept and 0.783 for beta 1. Thus, the resulting regression equation is y hat equals 16.609 plus 0.783 times our midterm exam average. Part F asks how the predictor influences the response. That is the interpretation of the coefficient for the midterm exam average. That's to say that with a 1 point increase in midterm exam average, we expect to see a final exam score increase of 0.783 points. Next, we're asked to analyze whether the average midterm exam is a significant predictor. To start, we define our parameter, in this case, beta 1, which is the population regression slope. Then our null hypothesis is that beta 1 equals 0, and our alternative hypothesis is that beta 1 does not equal 0, and then we have a significance level of 0.05. Our test statistic is beta 1 hat, which is the estimate for beta 1, divided by the standard error of beta 1 hat. The standard error in this case is again given in the table on the top of the problem. We see that the standard error for beta 1 is 0.05. Thus, we have a test statistic of 14.016. Step 3 asks for the corresponding p-value. In this case, is the rightmost value found in the top section of the output. In this case, it is all zeros, indicating it is below 0.001. Thus, since it is below our level of significance, we can reject the null hypothesis, and we can conclude that based on a random sample of 180 students, there is significant evidence at the 5% level to conclude that the midterm average is a significant predictor for the final exam score. Part H then asks us to predict two final exam scores based on midterm scores. In this case, we want to predict the final exam score for students who have received a 59 and 98 on their respective midterm averages. To find these values, we simply plug in the specified values into the regression equation found in Part E. Therefore, we have a final exam score of 62.81 for the student who had a 59 on their midterm, and 93.34 for the student who had a 98 on their midterm. Next, we want to find and interpret the value for the r squared. This, again, is found in the provided output, and we can see that it is a value of 52.4%. With that, we can conclude that the proportion of the observed variation in the final score can be explained through the regression relationship with the average midterm score is 52.4%. Finally, we are asked to estimate the standard deviation of the model. That means we're looking for the RMSE, or rather root mean square error, which we can calculate using some of the values found in the output above. If we scroll up to the top, we can see that in the table here, there is a mean square error associated with the residuals, has a value of 96. Taking the square root of that yields the root mean square error, which is the value we are interested in. Therefore, we have a root mean square error of 9.7979. So with that concludes our coverage of the practice midterm. I wish you well on the real midterm, and I will see you next week. Thank you very much for watching.